It's my pleasure to welcome you all here. Let me introduce myself. My name is Chitra Shankar from Department of Computer Science. My seminar topic is Direct Cache Memory. But today I'm not going to take any seminar. Instead of that, I'm going to say what I did after I got my seminar topic. First, I recollected what I know about the topic. I know that a cache memory is a memory where it stores frequently used data in the memory. And also I recollected the types of memory. Next I went to A to Z shop, which is nothing but Amazon shop, which says like A to Z all products will be available. So I want to know whether this cache memory will be available or not. So I just went and browsed for the cache memory in Amazon. So it also showed me some results. So I went and clicked one. So I just want to know its properties. So I just scrolled down and I saw what kind of RAM it uses. So this type of cache memory uses an SD-RAM. So I came to a conclusion that cache memory uses an SD-RAM. And then I had a question to myself. When there are so many types of RAM syndromes, why this cache memory uses particularly an SD-RAM? So to know the answer for that, I further browsed about RAMs. There is a kind of RAM which is called as DRAM, which means dynamic RAM, which uses capacitors to store the data, where these capacitors should be electrically recharged often in order to store the data. But at the same time, we have another option which is SRAM, which means static RAM. This static RAM is used in the cache memory. This RAM doesn't have to be refreshed oftenly like DRAM. It is faster than the DRAM, but at the same time it is little expensive than the DRAM. So again I had a huge confusion. In Amazon I saw like cache memory uses an SD-RAM, but at the same time in theoretical part I also saw about cache memory uses an SRAM. I had a huge confusion that whether a cache memory uses an SD-RAM or an SRAM. And then I came to know that a cache memory is an inbuilt one. So I want to know that an inbuilt cache memory uses an what RAM. So an inbuilt cache memory uses an SRAM. Whereas what we saw in Amazon was not an inbuilt cache memory. So it uses an SD-RAM. But by default, an inbuilt cache memory always uses an SRAM. Whenever we want to fetch some data, the CPU first checks whether the data is present in the cache memory or not. Cache memory says, no, the data is not found here. Then the CPU has to go to the RAM and fetch the data from the RAM. If the data is found in the cache itself, then it means cache hit. If the data is not found in the cache, then it called as cache miss. There are three levels in cache. They are level 1, level 2 and level 3. Now let's see about level 1 cache. Level 1 cache is also called as a primary cache. This level 1 cache is present inside the processor itself. So it works in the same speed as processor itself. Now let's see about level 2 cache. Level 2 cache is also called as an external cache, but it is present inside the processor itself. The data which were not caught by the level 1 cache will be caught in the level 2 cache. Let's see about level 3 cache. Level 3 cache is used in the dual core processors, where their cache is shared between the two cores of the computer. This level 3 cache is much bigger in size when compared to level 1 and level 2. But in case of processing speed, the level 3 cache speed is little low when compared to level 1 and level 2. So from this we can conclude that if size increases, the speed decreases. We have already seen that cache memory stores frequently used data. But from where this frequently used data will be fetched? These frequently used data will be fetched from the main memory. So there should be some sorts of communication between the main memory and the cache memory. Note an important point here. The cache memory just copies the data from the main memory, not take the data from the main memory and put it into a cache memory. Here my curiosity went very high. How this cache memory copies a data? In physical classroom, how we used to copy a data? We used to pass a paper and through our hands and we used to copy a data. But at the same time, how this cache memory copies a data? How the communication between the cache memory and main memory? How it will be communicating? What is happening between the cache memory and main memory? So we are going to see in detail about this. For our understanding, we are dividing this main memory into blocks. This one is called as a single block, and we are dividing this cache memory into lines. Always a block and the line will be in equal in size, and everything will be in equal. I'm just naming. For main memory we are dividing into blocks, and for cache memory we are dividing into lines. It's just for our imagination and for our understanding. This doesn't happen in a real time. It's for just our understanding. Now let's see, like, this main memory consists of 64 words. We are assuming like this main memory consists of 64 words, and this cache memory consists of 16 words. If you ask what is a word is the smallest addressable unit in the memory. Okay. Now we are assuming like a single block. A single block consists of 4 words. Only one block consists of 4 words. So in total, how many blocks we need if we have 64 words? So to calculate that, the total number of words divided by a single block consists of 4 words. So 64 words divided by 4 words, which is nothing but 16. So we need 16 blocks in the main memory to store as 64 words. So this is block 0. This is block 1. Up to it goes up to 15. Why it goes up to 15? Because we are starting from 0. So it goes up to 15. So total here, how much blocks? It's 16 blocks. And we have seen this main memory consists of 64 words. So here will be 0, 1, 2, 3. A single block consists of 4 words. So we are just numbering like 0, 1, 2, 3. And it goes up to the word 63. So now let's calculate how many lines we needed for a cache memory. So in here, total words is equal to 16 words. So 16 words divided by 4 words. 4 words means a single line consists of 4 words. So 16 divided by 4, which is equal to 4 lines. So this cache memory consists of 4 lines. Now let's calculate how many bits we needed for the 64 words. The CPU always converts into bits and only sent to the main memory. So how many bits we needed? How many bits does the CPU should give to fetch the data? So how we will calculate is, if we take 64, then we have to do this long division. So 2 3s are 6, 2 2s are 4, and the remainder will be 0. 2 1s are 2, 2 6 are 12, remainder 0. So 2 8s are 16, 2 4s are 8, 2 2s are 4, 2 1s are 2. So 1, 2, 3, 4, 5, 6. So 2 power 6 equal to 64. Okay, fine. So we need 6 bits. The CPU has to send us 6 bits to fetch the data. Now let's assume that the CPU has sent this 6 bits. So now what word it will be fetched from the main memory? Let's see how does it happen. So it first divides into 2 parts. The first part is called as the block number, and the second part is called as a block offset. This bit denotes number 5. How it denotes the number 5? If we take 5, 2 2s are 4, and remainder will be 1. So 2 1s are 2, remainder will be 0. So 1 0 1. Since it's in 6 bit, 1 2 3 4 5 6. So the number 5 in 6 bits, it will be denoted like this. Okay, that's the same thing here. In block number is used to identify which blocks does this data present. This here this block number is 0001. So this is 1. So in this block our desired data is present. So from this we can find out. And what is the data we have to fetch? This is 01. Okay, fine. So 01. So it will fetch data from here. So let's look into another example. This 10 represents the number 2. Okay. So this is a 6 bit. We are dividing into 2. One is block number and the other one is block offset. Block number is used to identify which blocks does the data is present. So from here we could find like in the block 2. So this is the block 2. We could find the data, and which data we are going to find. So that is also 2. So 0, 1, 2. So the data is, this is how the data is fetched from the main memory. But there is no communication between a main memory and the cache memory. We have only seen how to fetch data from the main memory if a bit is given. So here in lines, the block numbers will be there in the round robin manner, not in the normal manner. Not in the normal manner, it will be there in the round robin manner. It follows the round robin rule. Okay. So these 15 numbers, that is these total will be 16 numbers and the ending will be 15. Okay. And these are called blocks and these are line numbers. Okay. So now let's see the connection between the block and the line number. So the block 15913 will be fetched only from this line number 1. Like the same wise, the block 0, 4, 8 and 12 will be fetched only from the line number 0. So what is the speciality in it? When I came to know this, I just really admired a lot. How is this possible? The block 0, 4, 8, 12 will be there, right? So if we see the ending of block 0, 4, 8, 12, the last two digits will be same. That is 0, 0, 0, 0. If we take the block 15913, it can be accessed only through the line number 1. If we check the last two digits of 15913, that is 1 is 0, 1 and 5 is 0, 1 and 9 is also 1, 0, 1 and finally 13 is also ending with 0, 1. The last two digit will be same. The same case for line 2 and line 3. These four blocks, the last two digit will be the same. That's the speciality of this round robin manner. Due to this round robin manner only, these last two digits will be same. So total there are 6 bits. Last 2 bits is for block offset. And the first 4 numbers, we say it like a block number to identify the block. In that block number, we are dividing into 2. Okay. The first 2 bits is called for tag. We name it as tag. Okay. This last 2 bits you can see, no, these are ending with same ending. So these are called as tag. Okay. And this 2 bit is used to represent the line number. This is for block offset, this is for line number and this 2 bits for tag. So this cache memory has tags. Okay. So these tags consist of 0, 0. That is in previous we saw like last 2 digit will be same. So the common thing will be there in the tags 0, 0, 0, 1, 1, 0 and 1, 1. So these are the line numbers. So now let us write the bit here. Okay. So let's write for this. So the tag is 0, 0. So the first 2 digit will be 0, 0. And the line number is 0. So line number is also 0, 0. So in block offset, we could access 0, 4, 8, 12 blocks. Okay. 0, 0. Or we could have 0, 1. Or we could have 1, 0. So like that block offset will be changing. But tag, if you want to use this one, this tag is what? 0, 1. And this line number is also 0, 1. So tag, lastly block offset alone differs. After knowing all these things, I came to know this is called as direct cache mapping. And that's our topic. So this is how this cache memory and the main memory connects to it. And I also came to know that there are 3 types of mapping. One we saw is called direct cache mapping, and the other is called as associative mapping, and the third one is called as set associative mapping. Now let's see about associative mapping. In associative mapping, we have all same thing like tag, but the tag consists of 4 bits. In previous case, we saw like a tag consists of 2 bits, but here tag consists of 4 bits, and a single line will not have specific blocks. It will have like 0 to 15 blocks. Any blocks can be there in a single line. See how this works. Uh, as usual, here 4 bits for block number and the last 2 bits for block offset. Here this C is nothing but the comparators. This block number will be compared to the tag. So it first checks whether the first block number is present in this tag using a comparator. If it's not, then it moves to next one. Then searches whether this block number and this tag matches. If no, then next move to one. If no, then next move to one. So like this it searches. Here what was the problem arose was, if there are n tags, we need n comparators. So here the comparators we need a lot. Okay. And if anything says yes only, it will return yes. If anything one says no, then it should say no. So the time complexity is higher and we need more comparators. In order to overcome this problem, we have set associative mapping. Even though if we go to an hotel and order a set chapati, we will get 2 chapatis, right? So that's the same thing here. We are dividing the lines into 2. So that's the main target of set associative. So this is set 1, this is set 2, and this is set 3. We are dividing into sets. Here block number is 10. 10 specifies 2. So it specifies this second block, and it checks whether in the second blocks we have 2 tags. So here the tag mentioning is 0, 1. So it checks whether anything matches with this 0, 1. If yes, then it will be returning yes. If no, it will return no. So the advantage of this is the comparators use will be reduced. There is something called as 5 why technique. If you ask 5 whys to a problem and get solutions for 5 whys, definitely the problem will be solved. And that's how I started this seminar topic, and I learned all those things. And now I'm happy to say that I have finished this seminar. What is the takeaway for me is, there is a lot more to learn. I have just given a small input to you guys, and if you want to really know about more details about the catch memory, you can browse some more. I never thought that I would learn so much about the direct catch memory. So I just now realized that the more I learn, the more I realize how much I don't know many things in this world. So the more you learn, the more you will realize. I just realized this code today. That's the point I'm just going to say. And I thank you all for watching this video very patiently. I hope you guys got my input, and I hope you guys would understand the seminar. And I thank the ma'am for giving me this wonderful opportunity. Thank you all. Bye bye.